Okay, let's start today's session. Good afternoon, everyone. This is the 10th session for the NPTEL course Solid State Physics. The course instructor is Professor Amal Kumar Das from IIT Kharagpur, and I am a PMRF Research Scholar, a TA for this course. I am from School of Physics, University of Hyderabad. So, as you all know, these are sessions where we discuss that week's topic if some needs some clarification, and then we mainly focus on doing some relevant numerical problems. So, the same thing we'll do. And first, let's start with some quick revision of what were the things discussed last time. These are the books recommended for this course. So, last week we were discussing about thermal properties of solid. So last week we had discussed about various models which try to explain the thermal properties or the thermal behavior of various solids that is seen. So we had already through experiments there was certain behavior of parameters like specific heat capacity and other things that was seen, and then various models were given by different researchers over some time. One was like Dulong-Pettit law that we had discussed, according to which specific heat constant for every solid, according to that model, it had come out to be 3R, which is a constant, and this was able to explain the behavior of CV as a function of temperature only for high temperature, because at low temperature it's not constant. This was what was observed experimentally, that specific heat constant is not constant at lower temperature. So this model was only able to explain it at higher temperature. Then another model was given by Einstein where he had considered quantization, and then that was able to explain at 0 and higher temperature. But the T cube, so this behavior which is actually specific heat capacity at low temperature is proportional to T cube. This was not even obtained from Einstein's theory, and then third model or third theory had come by Debye, whose derivation or calculation could give a T cube expression. So these things we had discussed. The derivations you can see from that week's lecture, and we had just discussed these few points, and then we had done numericals based on this. So last week was about this thermal properties. Now another area under this solid state physics is on discussing magnetism or magnetic properties of solid, which is again very important property. So let's start with that. Yeah. So magnetic property, or like whenever we explain any magnetism or magnetic material, we know that we associate some specific observation with it, or what we see is that the materials which we call magnetic, they attract or repel certain kind of material, and then based on that interaction is what we usually see around, that we tell if it's magnetic material. Usually the magnets that we see around us, they attract certain kind of material, not all material, and then we say that there's some sort of interaction between that material with other material. Again, we cannot see that, it's not like they have to be connected or in touch to be putting force on each other, but this is observed that even if there is some gap between them, we see that interaction between them. That comes, we'll see what is the origin of different kind of this magnetic force also. But first, I think, because even the derivations were done in this week's lecture, you must have seen or you can see from there. So in today's session, we'll again just discuss some few, what we say, these terminologies which are important to understand magnetism topic. So we'll start with that. Like the first question, or the first part of the lecture was on explaining what is susceptibility, permeability, and the terms like magnetic field lines of force, or magnetic flux density also it is called, or magnetization or intensity of magnetization. So we know this law that whenever we have a current carrying conductor, there is a magnetic field generated around it. And this field is, okay, we have two terminologies in magnetism. One, we say B, is also sometimes used to denote magnetic field, and sometimes we use the letter H for the same. To understand the subtle difference between this, although sometimes it is very commonly used interchangeably also, but if we want to understand whatever small differences between them, we need to see that H is usually, to just put it in simple words, H is the field that is applied to a material, or maybe the material is in the field of intensity. That field we represent H. Like here, if I have a current carrying conductor, then it will have a magnetic field around it. Now that field we can call magnetization field, or its magnetization field, or it can be also called actually magnetic field, magnetizing field, or intensity of magnetic field. Intensity of magnetizing field. This is the field that we usually, when we apply to any material, the response of that material is what we get as B, which is either called magnetic flux density, or it's simply magnetic field, or also magnetic induction. Because the definition in physics or solid state physics, if we'll go, different people define these two things differently. Even in CGS and MKS units, we have different units, and sometimes they can be considered equivalent. Sometimes there is a constant with which we can change from one to another. So that's why simply, if you want to understand, there is several definitions for B, like magnetic lines of force per unit area. Also, it's defined in this way. To just keep the difference clear, we can understand that it's also called magnetic field induction, magnetic induction. We can understand it like this, that we are applying a field, maybe depends on the source, maybe we have a current carrying conductor and around it the field is this, and if I'm keeping my material here, then H is the field we are applying to this material, and it's responding, and there is a field that gets not generated, but depending on what kind of material it is. And this was also discussed in the lecture, that materials have something called magnetic dipole moments. Depending of what kind of material it is, the moments interact with this field H, and then there is a field induced in this material that we denote by this capital B, and that's why we call it as magnetic induction. And this H is called magnetization field, means the field that we are using to magnetize a material. Now it depends how much it will get magnetized. That is the like property or characteristic of that material, because different materials have different strength or different intensity to which they may respond to the material. Some may get aligned or attracted, some may repel this H, and we'll see we have some materials which when placed in magnetic field, the magnetic lines of force tend to pass through them, and sometimes we have materials when these magnetic lines of force tend to avoid passing through them. So different materials respond to the same H, same magnetization field is different, and because their response is different, the B or the magnetic induction in them is different. So I could be using the same H, like the same magnetization field, but depending on what kind of material I am applying that field, the B for them will be different. That we'll see depending on what is the permeability or susceptibility of that material. The magnetic field or magnetic induction in those materials will be different. So I'm not sure if it's still clear, but if you guys have doubt, you can ask or we can discuss. But I just tried to make this small difference that H is the field that we are applying, and we call it magnetization field because this is the field we use to magnetize that material. It gets magnetized or not, that's different thing, but this is the field we are applying. And how the material gets influenced, then it responds, and then there is magnetization induced in that material. So there is some difference between H and B. And that's why this magnetization field is also called intensity of magnetization field, that how much strength or what is the magnitude of this field is that we are applying or it's there. Okay, so this was about the difference between B and H. I think we can discuss this. There's something. Yeah, so like this is a graph between B and H. Usually this is the SI unit for magnetic flux density or whatever name we want to call. Its SI unit is Tesla, whereas this magnetizing field, its SI unit is ampere per meter. In CGS, for magnetism, even CGS units are very commonly used, unlike other areas of solid state physics, I think. So, and for this, it's usually EMU per cc or EMU per gram, depending this is for magnetizer or state. For this is Gauss. Okay, so what we see here, definitely B and H is not the same quantity or a thing, because we see, so this is what I was saying, on x-axis we have H, the field that we are applying, and this loop is for some material, we don't know, but here we are applying certain field, this H we are applying, and then the material, depending on its property, it's behaving or responding to that H that we have applied, and this is the field induced, magnetization induced in that material. So we can see, like, for this value of H, whatever it is, 25 or something, the magnetization induced is, again, the units are different, so even the magnitudes are on different scales. But so I just hope this B and H thing is clear, that they are not the same property, although sometimes they get used interchangeably because there is difference, and the difference was H is the field we apply to the material and B is the magnetization induced in the material depending on its property, that how it's responding to the H, and that's how we get this BH curve. Okay, anyways, I think this is done. Yeah, so depending on, as I said, the property of these materials, We characterize them by, we have two terms by which we characterize these different type of materials, magnetic materials that I'm talking about. One is susceptibility, magnetic susceptibility. I'm not adding the word magnetic everywhere, but because we are discussing magnetism, so just keep in mind we are talking about magnetic susceptibility, and when I'll be talking about magnetic moment, dipole moment, that will be magnetic moment only, because we have similar things in when we discuss dielectric properties. So don't get confused. Like I'll just drop magnetic word, but magnetic susceptibility, magnetic permeability is what we'll be talking about. So susceptibility and permeability. These are characteristics of those materials which control or which drive that how that material will respond to the H that we are applying, and that will result in what is the strength of B, or the magnetic induction that gets induced in that material. Okay, now so okay, we can, let's see what is this. Maybe before that, so okay, without first going to the definition of permeability, as I was saying, some materials uh, when placed in magnetic field lines, the magnetic lines of force avoid to pass through them. So in this case, the magnetization induced magnetic flux density of that material will be less than what I had applied. Whereas some materials, the magnetic lines of force tend to pass through the material, and in that case, because okay, this, you must have already seen this in this week's lecture, the relation between B and H also, that this is the relation, and depending on what is the value of mu, which is permeability, the B is what is the response to H. So for materials where permeability is less than 1, although this is relative permeability, but I think we know this permeability is actually the product of relative permeability and permeability of free space. So it's okay, fine. In free space or in vacuum, we'll just write it like this. Mu naught will be permeability of free space. Here, if we are talking in a material, then we can just replace it using mu. Anyway, so if the material's permeability is less than 1, then of course the magnetic field induced in the material will be less than what the field we had applied. And this happens when the magnetic lines of force avoid going through it, or the material's response is such that magnetic lines of force don't pass through it, and such materials are called diamagnetic material. Another type of materials where magnetic lines of force tend to pass through it are materials for which permeability constant has value more than 1, and because of that the magnetic induction is like more than what I had the magnetization field that we had applied. And as you can see, the even like the magnetic lines of force go through them. It's like magnetic flux density increases here. I told like B we also call magnetic flux density. And then we have some materials for which permeability constant has very large value, and they are called ferromagnetic or ferrimagnetic, depending again. And for them, this magnetic flux density is even higher. So here, if we say the same H I had applied for both, so again, I'm saying the same thing, but the magnetization field was same, but think it like first I kept this diamagnetic material in the same magnetic field lines, and in one case the magnetic flux density was less, one case it was more, one case it was even higher, all because depending on what kind of material it was, the response of that material for the same H was different. So this is what makes clear that B and H are different thing, and this is the difference. Okay, so permeability and susceptibility, let's discuss that. Magnetic permeability, which we represent using mu symbol. Mu symbol is used even in magnetism for various things. Sometimes we use it for magnetic moment also. So don't get confused, but we represent usually mu permeability also. Okay. So magnetic permeability is a fundamental property of any material, as we just now discussed. It depends on what kind of material it is, and it describes their ability to allow the passage of magnetic flux, magnetic field lines, or magnetic flux. This is what we saw. Permeability is characteristic of a material, that how it allows, or how easily it allows the magnetic fields of lines, magnetic field lines of force to pass through it. This is in simple terms. If we'll go, we can define it as using in terms of B and H. That is quantitatively, we don't need that. Qualitatively, to understand, for clarity, it is the ability, we can say it's the ability to, for a material, how easily it will let the magnetic lines of force pass through it, as we saw, which was higher for paramagnetic and ferromagnetic material, whereas lesser for diamagnetic material. It is defined as ratio of magnetic flux density. Just now, magnetic flux density is B. So it is the ratio of magnetic flux density to magnetic field strength. As I told, we call it magnetization field or magnetic field strength or intensity of magnetization field. They're different terms, but just keep in mind it's the same thing. So we define mu as this, that how much field I am applying and how much magnetic flux is getting induced. It's ratio of that. And yeah, the symbol is mu. And yeah, in simple terms, it quantifies how easily a material can be magnetized. So this is what we are trying, that when we apply H, which we are calling sometime magnetic field strength or sometime magnetization field, then how much field we are applying. Permeability tells how easily that material can let the magnetic lines of force pass through it, means how easily it get magnetized in influence of that magnetization field around it. Materials with high permeability allow magnetic lines of force to pass through them more readily than materials with low permeability. This was what we saw in this figure, that a material which will have permeability less than 1, but it will kind of not avoid for magnetic lines of force to pass through it, whereas in materials where magnetic permeability is more than 1, the magnetic lines of force, it will allow the magnetic lines of force to pass through it more. And for materials which have even higher value of this magnetic permeability, for them this B is even higher. That means their ability to get magnetized is higher. So permeability in layman terms is just telling us how easily material gets magnetized. So if a material's permeability value constant is higher, that means the more readily, the more easily it will get magnetized in presence of magnetization field around it. Next is magnetic susceptibility. We usually represent is using the Greek letter chi. Magnetic susceptibility is also a property of materials, describing their ability to become magnetized in the presence of external magnetic field. So again, even this susceptibility, permeability, although sounds similar, small differences. Magnetic permeability, we usually keep it in terms of how easily it allows the magnetic lines of force to pass through it, and susceptibility is its ability to become magnetized. Ultimately, it's leads to same thing, because even permeability and susceptibility are related, and the relation between them is, I think, mu is equal to, yeah, chi is equal to mu r minus 1. So they are related. That's why these two um, these two parameters are also related and similar, because if susceptibility is higher, means ultimately it means the material will get magnetized very easily, and the same thing with permeability. But usually with permeability we define that how easily the material lets the lines of force pass through it, and susceptibility is the easily it will let the magnetic lines of force pass through it, means that easily it will get magnetized. It is also, yeah, it is the ratio of material's magnetization to applied magnetic field strength. So when we apply magnetic field, the magnetic moments align, or again depending on the material, then we get magnetic moments per unit volume. This is the ratio. It is given by letter chi. Magnetic susceptibility can be positive, negative, or zero depending on the material, and accordingly we get permeability more than 1 or less than 1 or even greater than 1. Materials with positive magnetic susceptibility are attracted to a magnetic field and tend to become magnetized in the direction of applied field. In contrast, materials with negative susceptibility are repelled. So it's the same situation. What happens here? Because the permeability allows lines of force to pass through it, so susceptibility here, permeability if is less than 1, we know mu r minus 1 is the relation. If permeability is less than 1, then susceptibility will be negative. That means permeability is telling us how easily the lines of force will pass through that material, and because permeability is less than 1, it means there are less, not chance, but the material will be not easily letting the lines of force pass, and because of that the chi will be negative, means the chances of this material getting magnetized is less, or negative is the constant value. And when the permeability constant is more than 1, then this will be small, but it will be positive. In that case, when permeability will be more than 1, it will be positive. It means it has better chance of getting magnetized, this material we are talking about, because the susceptibility, permeability are the properties related to that material. And then when permeability is even higher value, then the susceptibility will be positive, as well as it will have a very high value that shows its readiness, that how easily it will get magnetized. Okay, so this was about susceptibility and permeability. This is just the difference. Again, if we revise it again, magnetic permeability is a measure of how easily a material can become magnetized in presence of external magnetic field. Magnetic susceptibility is, yeah, this is again another thing. Magnetic susceptibility is a dimensionless constant. Okay, yeah, I forgot to tell you about the units. Magnetic permeability, it's SI unit, if relative magnetic permeability, or even permeability in free space. The SI unit for them is Henry per meter, or Tesla meter per ampere. And for susceptibility, it's dimensionless quantity. Okay, so what is this? Even these units change a lot when we go from CGS, like centimeter, gram, second, that unit, to meter, kilogram, and second thing. So things which could be equal in CGS may not be so when we go to MKS. This is small, little confusing in magnetism, but I think for our discussion we don't need to bother about that. Yeah, so It was already discussed in detail, all the different type of magnetic materials that are there in yeah, the major kind of I think two, paramagnetism and diamagnetism, were discussed in detail in at least this week's lecture. So derivation and everything is there already. We'll just discuss, have small discussion, because I think mainly we'll go to our numerical problems. So diamagnetism is a type of magnetization in which is present in actually all the materials, because its origin is the orbital angular momentum. The reason is that in any atom of any material, we have nucleus where we have proton, neutron, and then around it, at least this is how we classically define, that around it electrons are revolving, and because of this motion, we know when we have a current carrying conductor, there is magnetic field around it. The same thing applies here. When electron is moving, it's like a current flowing, and because of that, we have magnetic field. And that magnetic field, we can think of this electron revolving around nucleus as kind of one current carrying small loop, and because of that current carrying small loop, we'll have magnetic field around it. So as we see, when we have a magnet bar, when we place a magnet bar in presence of some another magnetic field source, so that magnetic bar or magnet, it deflects. The same way, if we are considering this is a current carrying loop, and it has a magnetic field, and then if we apply a magnetic field, or we keep this, we cannot individually, I'm talking about atom here, but it's just like keeping a material. It has lot of atoms and they will respond. Here we are just taking one particular atom. So because it has some magnetic field, so when we'll place it in a magnetization field, it will interact, and that interaction again depends on that type of material we are talking about. So what is observed is that, like we discussed, there is ferromagnetic or ferrimagnetic material or paramagnetic material which easily get magnetized. They have permanent magnetic moment in them. They also have another theories for their origin. But when we have materials for which these for which the magnetic permeability or susceptibility is, like, permeability is not more than 1, susceptibility is not positive, then still they all show diamagnetism, because diamagnetism is like present in every material, because this kind of electron is happening because of this motion of electron around it, which gives orbital angular momentum. And then you have seen the derivation in this week's lecture already, that how we get a term from it which tells us the magnetic moment induced in the diamagnetic material. And the expression, if we write, so for when we are talking about diamagnetism in any material, it happens because electrons are revolving around the atom, and because of that we get orbital angular momentum, and the magnetic moment induced because of this is, the expression is, the derivation you have seen, so I'm just writing the final thing. So this frequency is 3/2. So the magnetization for that particular material will be a number of atoms in that material and the atomic number of electrons, the atomic number of that element, and then this mu. And then if we put this also, then it will be E square R square B by 6. So this will be the diamagnetic or diamagnetic magnetization, which is present in every material. Whereas, so if usually what we see is in our daily life, we see a bar magnet attracting some kind of material, and then we say it's magnetic. But that is actually, that material is showing ferromagnetism, because its magnetic permeability uh, is so high that it's being able to get attracted to that bar magnet. But not all materials show ferromagnetism, or because not all materials magnetic permeability is high. So even if the material is not showing ferromagnetism or paramagnetism, they all have diamagnetic property. But the thing is, diamagnetism is a very weak kind of magnetism, and because of that, if a material shows paramagnetism or ferromagnetism, then we don't see this. But if it doesn't have, usually we call such materials non-magnetic when they don't show paramagnetism or ferromagnetism, means we cannot actually see them getting attracted or responding to the magnetization field we are applying. So we may label them non-magnetic, but still they always have they always show diamagnetic behavior. But because its strength is very less, so that's why it gets hidden, or it's not able to present itself when other kind of magnetism are dominant in materials, like in iron or something. Ferromagnetism uh, is very strong. That's why diamagnetic behavior, which again we'll see what kind of different we can discuss, like the behavior of magnetization versus H. That if I'm applying some field, how much it's getting magnetized. For diamagnetic material, the behavior is, because we saw that for diamagnetism material, permeability is less than 1 and susceptibility is negative. So it avoids and it repels the field that we are applying. So its behavior is, sorry, it's actually, sorry, it's passing through the origin and it is linear, and slope may vary depending on what kind of material it is and what is the value of susceptibility, because M is chi times H, and for diamagnetic material chi is negative, so that's why the slope is like this. But this behavior we may not see for iron because the dominant is ferromagnet. So what I wanted to say is that diamagnetism is innate property of every material, but it gets overshadowed when other kind of magnetism is also present, like ferromagnetism, antiferromagnetism, ferrimagnetism, or paramagnetism, because they are very much like their strength is much higher than diamagnetism. Okay. So another thing, diamagnetism is we can see from expression, and if this is the expression for magnetization in a diamagnetic material, and susceptibility, which is M by H. So when we will take here, B is mu H. No, B is mu H. So if I replace mu H and then divide by H, I'll be left with just mu. Overall in this expression, I see no influence of temperature, and that is what is seen, that diamagnetic behavior of any material is independent of temperature. So at any temperature, the diamagnetic influence is same. So for diamagnetic material, susceptibility or permeability is independent of temperature. There is, okay. When we discuss paramagnetic materials for which susceptibility is more than 1, permeability is more than 1, but this is positive, and permeability is more than 1. So the magnetic lines of force tend to pass through such materials. And magnetic flux density is more inside the material. Outside the material, the magnetic flux density will be given by this, where this is permeability of free space. Inside the material, these are continuous actually. They're just getting more, they tend to pass through the material, so magnetic flux density here increases. That is what it means for paramagnetic materials. And inside the material, because it's not free space, we write magnetic flux density is equal to this mu and h, where mu is mu naught mu r. This is relative magnetic permeability. Actually, it's mu r is mu over mu naught. Okay. So, and to explain what is the origin of paramagnetic behavior in any material, again there were different theories. Like this was discussed in the lecture. You can refer from there. One was Langevin's classical theory. From which the term for magnetization in a paramagnetic material was derived to be depending on number of atoms and then magnetic moment, the field, magnetization field, and it also depends on the temperature. From this, we can find out the chi. So it will be, chi is m by h, so the expression will be n mu square mu naught divided by 3 kBT. So we can see the susceptibility for paramagnetic materials do depend on temperature, and so it does depend on temperature. And if we plot chi versus T, because they are inversely proportional, the graph will be something like this. Or if we take 1 over chi and T, then it will be a straight line. So this is the behavior. For diamagnetic material, the susceptibility was independent of temperature, whereas for paramagnetic materials, it is inversely proportional. So the derivation till here. Yeah, so this was Langevin's classical theory. Another discussion was on the quantum theory, how it explains the magnetism, the paramagnetic behavior. And from that also some expression, because there we consider that, okay, so we know in paramagnetic material, we talk about magnetic moments. We usually represent using these arrows. So these are the magnetic moments, magnetic dipole moments, or sometimes we just call them moments. And when we apply magnetization field to that material, these magnetic moments which are associated with the electrons. So all these discussions were again in the lectures. So I'm just straightforward going to the discussion. All these electrons or the atoms, they have these magnetic moments. For diamagnetism, these magnetic moments tend to repel the applied field, that is through Lenz's law, another aspect. But for paramagnetism, we have permanent magnetic moment, unlike diamagnet, because in diamagnetic materials we don't have unpaired electrons. Because of that, means the electronic configuration of those materials are such that the electrons are in pair, and because of that there is no net magnetic moment. So only source of that diamagnetic behavior is because of the orbital angular momentum, that is the motion of electron around the nucleus. This is how, at least in classical theory, we define. Whereas in paramagnetic material or other different magnetic materials, we have permanent magnetic moment because we have unpaired electron. But until we apply the field, these magnetic moments are randomly oriented in any random direction. Because of that, even if you may be holding a paramagnetic material, you may not see it attracting or interacting with another iron or any kind of another material, because since they are all randomly oriented, they nullify each other. But as soon as we place it in a magnetization field, they all interact and align with this H, and then this will be the magnetization behavior with respect to the field we are applying. The slope again will depend on what is the strength of susceptibility in that material, but it will be a linear, linear behavior, because when we apply the field, they all will align along this direction, and then we'll get magnetic field around it. This is what happens in a paramagnetic material. And then in ferromagnetic material, what I was telling is, so in classical theory, when we had, as you would have seen in derivation, we were taking the alignment of these magnetic moments with H. There could be slight deviation, and we were taking the angle the magnetic moment makes with the field. We're taking it from theta to d theta, but it can take any value, is what we were considering in classical explanation. But when we were considering quantum theory for paramagnetism, there we take that even these values are quantized, and so the derivation is little different, but we get the same result as far as the dependence of susceptibility on temperature is concerned. From that also we get the same, that susceptibility for paramagnetic material is 1 over temperature. Ferromagnetism we can discuss, but I think that is there for next week. But still, so how something different is going on inside a ferromagnet, or let's not go into ferromagnet or ferrimagnet, maybe those things we can discuss later. But just to start about ferromagnet, in diamagnetism we saw electrons are paired, so no net magnetic moment, and only because of orbital angular momentum there is diamagnetism in that material. In paramagnetism we saw we have unpaired electrons, thus we have net magnetic moment. Magnetic moment is not zero, and that magnetic moment interacts with field and get aligned along with the field. Now in ferromagnet, what happens? Even in absence of the field that we are applying, these materials may already have the magnetic moments aligned, and because of that they may already, so that's why we say ferromagnetic materials are materials which have we use a word spontaneous magnetization actually. In paramagnetic materials, material gets magnetized when we apply field to it. But in ferromagnets or ferrimagnets also, even in absence of this magnetization field, due to some reason we'll discuss next week, the moments are not randomly oriented, they are already aligned. And when we apply field, the permeability, because they are already aligned, so their response is even stronger, and that's why the magnetization for ferromagnets, okay, because of hysteresis, the loop is actually we see something like this. If I make it like this, when we apply field, because there is something known as domain, again I think we'll be discussing next week, we get a very high magnetization response, but the loop actually looks like something like this, unlike paramagnetism, for which it was just a linear response. So in detail we'll be discussing next time, but just to tell what is the difference, one basic difference is that paramagnetism, the moments are in absence of field, they are randomly oriented, and only when we apply field they get aligned and they get magnetized. Whereas for ferromagnets, even in absence of any field, due to some interaction, they are already aligned. So this was it. And I think now we can move to discussing more the numerical problems. If you have any question, you can ask, we can discuss, or otherwise we will start numerical problems. And the derivations are very well done in all this week's lecture. If you have any doubt, maybe we can discuss next time. First you go through that lecture. I think things will be clear. Okay, let's start with the problems here. So the first question is, diamagnetism is exhibited by, the options are only those materials which do not possess permanent magnetic moments, all materials, only those materials which possess permanent magnetic moments, only those materials which have strong internal fields. I think the best answer will be all materials. As I said, only they are not able to to show themselves, or we don't see because the strength is very less when other kind of magnetism is there, but otherwise diamagnetism is there in all the materials. So B is the correct option. Paramagnetic materials, when placed in a magnetic field, we're talking about paramagnetic materials. So when paramagnetic materials are placed in a magnetic field, they get feebly. So feebly means weakly. Weakly means less in strength. So they get feebly attracted, feebly repelled, strongly attracted. So we know paramagnetic materials, their permeability is more than 1, susceptibility is positive, and magnetic lines of force tend to pass through them when placed in a magnetization field. So they get attracted. Weakly or strongly is like relative terms. Strongly attracted, if we consider ferromagnetic materials get strongly attracted, then I think we can say that paramagnetic materials, we can say they are feebly attracted when they are placed in a magnetic field. I think A is the correct option. Next question is the net spin magnetic moment of Fe3 plus ion is, although it's given, but like Fe or iron, its atomic number is 26, and if we write electronic configuration, it will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6. And here we need the electronic configuration of Fe3 plus, means 3 electrons are less. So electronic configuration will change to 1s2, 2s2, 2p6, 3s2, 3p6 and 3d5, because these 3 electrons will get removed from this d and this s, because this is the outermost shell. So 2 electrons will get removed from here and then 1 will get removed from here, and also it leads to stable electronic configuration. So anyway, so all these are like inner shell electrons, they are all paired and all. Only this 3d has unpaired electrons, and for calculating the net spin magnetic moment we need the number of unpaired electrons. Unpaired electrons in that ion. So here for Fe3 plus 3d5, we know d has 5 orbitals. So we have 5 orbitals and there are 5 electrons, and from Pauli's exclusion principle, they will be arranged like this. And yeah, so number of unpaired electron here will be 5. Now the formula for spin magnetic moment is, if I denote this by n, then n plus 2 times Bohr magneton. This Bohr magneton also is explained in detail, in small derivation is there in the lecture. It is the magnetic moment of electron, and then Bohr magneton, its value is I think 9.27 times 10 to the power minus 24. I'm forgetting the unit also. Ampere per meter, ampere second. 9.27 10 to the power minus 24. Anyway, we'll see this later. But yeah, so this is like the magnetic moment of one electron that we say represent by this arrow, and the magnetic moment of the whole atom we express in terms of Bohr magneton, means in terms of magnetic moment of one electron. And if electrons are paired, then the magnetic moment nullifies. So only we are concerned with number of unpaired electrons in that atom or that ion. So like here, if it's 5, then this is the magnetic moment of Fe3 plus ion. This will be root of 35. It will be, sorry, I think less than 6, because 6 square 36. I think, let me just root of 35 is 5.92, and Bohr magneton is there. 5.92, or I don't know, we can round it off maybe. So in the option, I don't know why the option is not matching. This is the formula, and I don't know, I think the best answer would be then this. Maybe they have only considered the integer part for some reason. If we have to choose from these 4, then 5 Bohr magneton should be correct. But actually the answer would be 5.92 Bohr magneton. 6 Bohr magneton is not there. Maybe, I don't know. But here, if we have to choose the best out of these 4, then this should be the correct answer. Okay. Next question is susceptibility of diamagnetic material. So susceptibility, if you remember, we said susceptibility with temperature. Susceptibility is negative for a diamagnetic material because permeability is less than 1 for a diamagnetic material. So susceptibility is negative, but it's independent of temperature. That's a constant. So susceptibility of diamagnetic material is independent of temperature. It does not depend on temperature. So D is the correct answer. Calculate the diamagnetic susceptibility, that is susceptibility per kg mole or molar susceptibility of helium atom given its atomic radius is, the average atomic radius is 0.53 angstrom. We need to calculate diamagnetic susceptibility. For that we need diamagnetic susceptibility. The formula is minus mu naught E square and the average atomic radius R square, atomic number, and N is the number of atoms per unit volume, divided by 6m. Okay. The m is the mass of electron. This is the formula. Here we can substitute all this here, and now mu naught okay. Here we N is the number of atoms per unit volume, but here if we substitute N is equal to Avogadro number, we'll get molar susceptibility, so we'll do that. And let's keep this. Okay. Minus mu naught E square. Mu naught is, either we can write it as mu naught is permeability of free space. Its value is 4 pi 10 to the power minus 7, and then whatever unit, I don't remember some unit. So this will be 4 pi 10 to the power minus 7. E square means the charge of electron, 1.6 times 10 to the power minus 19 square, and radius is here in angstrom. So as I tell you every time, it's better to keep all the units in one system, because here other things we all are keeping it in meters and things. I think this also we should keep in meters. So this will be 0.53 and angstrom will be 10 to the power minus 10 meters. So putting that here, 0.53 times 10 to the power minus 10 and square, 10, multiplied by atomic number. Since it is for helium, atomic number is 2, and here we'll put Avogadro number, which is 6.023 times 10 to the power 23. So that we are done with numerator, and this negative sign is there, and then in denominator 6 times mass of electron, which is 9.1 times 10 to the power minus 31 kg. And when we'll do this calculation, let us calculate. For all these calculations, you guys can use calculator, because in exam as well, you are going to be provided with, because it will be online exam and you will be given online digital calculator. Only some places you need to remember values of such constants. Maybe it's not always given in the question. Value of Avogadro number or value of mass of electron or charge of electron. Sometime in some questions these values are given, but sometimes they are not given. So it's better to remember these values. And we'll do 4 times pi times 6.43 times 2 times 6.38 divided by 6 divided by 1. Minus 1.9937, and the powers 10 to the power minus 7. So I've just calculated all these magnitudes. Now we'll take care of these powers. So it will be 10 to the power minus 7 and 10 to the power 19 times 2. It will be 38. Okay. And then 10 to the power minus 20. To the power 23, and in denominator we have 10 to the power minus 31, which when it will come to numerator it will be 10 to the power plus 31. Okay. This will be 1.9937 and these powers will be minus 7 minus 38 minus 20 plus 23 plus 31. This will be 10 to the power minus 11. Did I do some? Okay, one mistake happened here. The Avogadro's number, we say this is in gram per mole. So 6.023 10 to the power 23 gram per mole. Here we are changing everything in SI units, so we need to change this gram into kg. So then this will become 10 to the power, this will not be 10 to the power 23. In kg per mole, it will be 10 to the power 26 because 1 kg is 1000 grams. Then this will be 10 to the power 26. Okay. And then this will be 10 to the power 26. Because of that, the power will be, when we correct this will be 10 to the power minus 8. 10 to the power minus 8 per mole. So this is molar susceptibility, so that's why per mole. And this will be the value, minus 1.9937. Susceptibility is negative. Maybe they have dropped the negative sign. I don't know. But the magnitude is matching this here. Susceptibility is negative, and then the value will be 1.9937, 10 to the power minus 8 per mole. Maybe they have dropped the negative sign. Okay, next question is magnetic susceptibility of aluminium at room temperature is this. Susceptibility is this at room temperature. Calculate its magnetization when a magnetic field of 0.5 Tesla is applied. See, that's why when in the beginning I was explaining the difference between H and B, I just keep the meaning clear in your mind, but I told you everywhere in magnetization or magnetic what this field when where we study magnetic properties, these terms are used interchangeably. So although I was explaining you several times that H is the field, magnetization field that we apply, and B is the response of the material to that H, still you will encounter several places where the term is used, like when magnetic field of 0.25 Tesla is applied. B is like the response of the material, but still this is the B here in the question they are saying is being applied. So although these two things are not same, but everywhere you'll find this kind of usage. So just get used to it. This is what I will say. And because you know it's in Tesla, that means it is this B that we are talking about. Okay. So we have to calculate magnetic susceptibility, and the formula of magnetic susceptibility, is mu naught M by B, and M is the magnetization, B is the magnetic field as per this question. Chi is this, and okay, let's calculate. So magnetization, wait, you have to calculate magnetization. So magnetization will be chi times B by mu, and chi is 0.82 times 10 to the power minus 8. Magnetic field is 0.25 Tesla divided by mu naught. Mu naught is 4 pi 10 to the power minus 7. When we calculate this, 0.82 times 0.25 is divided by 4 divided by 5. This will be 0.0163 and 10 to the power, okay, minus 8 plus 7 means minus 1, means 0.00163, or we can write it like this, 10 to the power minus 1. So, okay, just so this is 0.0163 10 to the power minus 1, or we can write it like 1.6 into 10 to the power minus 3 ampere per meter. This is the magnetization. This is the correct answer. This is the answer, but we have to put it in the form given one of the options should match. So this is the, we'll just change the place of decimal points and it will match the answer. So C is the correct answer. Next question, question number 7. Calculate the saturation magnetization of gadolinium. Basically, we have to calculate magnetization of gadolinium given that Bohr magneton is, so this is the unit of Bohr magneton, magnetic moment of electron, ampere per meter square. Atomic number of gadolinium is 64. Atomic weight or atomic mass, different things we call, 157.25. Density is given, electronic configuration is given. So to calculate the saturation magnetization, first we need magnetic moment. For gadolinium, the electronic configuration, gadolinium's atomic number is 64. So the electronic configuration becomes like if we write in terms of xenon, because xenon's atomic number is 54, it's a noble gas, and then 6s2 4 5 7 5d1. Here we see the unpaired electron is in 4 5 7 5d1. These are the outer shells in which we have unpaired electron. And F, we know it has 7 orbitals. Yeah. So all the orbitals are singly occupied by electron. That means no pairing is there. Then in D, we know there are 5 orbitals, and there is only one in it. So total number of unpaired electrons will be 7 plus 1, that is 8. We have total 8 number of unpaired electrons. And then the magnetic moment, how we calculate? Under root n plus 2 times Bohr magneton. So this will be under root 8. 8 plus 2 means 10 times Bohr magneton. This we will use to calculate the spontaneous magnetization in this question. These values we can put at the end also, so it's okay. Next thing that we need is to calculate the number of atoms per unit volume. Per unit volume. We need to calculate magnetization, it is magnetic moment per unit volume. And this we know relation between density and number of atoms and atomic mass. So from that, this will be density is given, because these relations we have used long back several times, so I hope you remember. And density is 7.86 10 to the power 3 kg per meter cube, and Avogadro number 6.023 have they given. 6.023 times 10 to the power 23 divided by volume. Oh, anyway, we are calculating number of atoms per unit volume, so this will be atomic weight. Atomic weight is 157.25. Now this is in gram per mole. Gram per mole, and when we change it to kg per mole, this will be 10 to the power minus 3 kg per mole. Putting these values and calculating 7.86 times 6.02 divided by 157.25, 0.3009, and powers will be 10 to the power 3 plus 23, and this, when it will come to numerator, it will be plus 3. So this is 0.3009 times 10 to the power 29 per meter cube, because we are calculating number of atoms per unit volume. And then when we calculate saturation magnetization here, it will be the number of unpaired electrons here, this magnetic moment thing. Bohr magneton, which is 9.7 10 to the power minus 24 multiplied by this 0.3009 times 10 to the power 29. This is 2.23 times 10 to the power 6 ampere per meter. B is the correct answer. Yeah, next question. A paramagnetic salt contains 10 to the power 26 ions per meter cube with magnetic moment of zero point 0.1 Bohr magneton. Calculate the magnetization of salt. We need to calculate magnetization in a field of 1 Tesla at 300 Kelvin using this relation. This is from the quantum theory of paramagnetism, like quantum, where we a quantum model or quantum theory of explaining the origin of paramagnetism. There we get, if you will see the derivation in the lecture, you'll see this kind of expression for magnetization. Okay, so this term we have, this expression or equation we have to use to calculate the magnetization, and so it's yeah. So we need to calculate this. First, let's calculate this mu b divided by Boltzmann constant in this. Magnetic moment is 0.1 Bohr magneton, that is 0.1 times 10. Bohr magneton is 9.27 or 9.24. Bohr magneton is 9.27. Okay. 9.27 times 10 to the power minus 24. Magnetic field is 1 Tesla. Again, here they are saying the field is 1 Tesla. Maybe it's induced field also, that is as a response of the property. But anyways, it's in Tesla, so it's B. And then Kb, Boltzmann constant, will be 1.38 times 10 to the power minus 23. And the temperature is 300 Kelvin. Always keep in mind for all these numericals, for any kind of numericals actually, it's always best to keep the temperature in Kelvin. So anyway, here already it's given in Kelvin, but if it's just mentioned room temperature or 27 degrees centigrade or something, convert it into Kelvin first and then use it in the calculation. With this, we'll get the value 0.1 times 9.27 divided by 1.38 divided by 300, 2.2391 times 10 to the power minus 24 plus 23 means 10 to the power minus 10 to the power minus 24, 10 to the power minus 23. Just a minute. 0.1 times 9.27 times 1. Tesla is also correct. Divided by 1.38 divided by 300. Okay, so this was 10, the answer was 10 to the power minus 3. And then when we take care of these powers, it will be 10 to the power minus 24 plus 23 means minus 1. This will be like 0.2, no, 2.2391 times 10 to the power minus 4. Okay. This will be this expression. Now we need to further calculate all this. N is given, mu is given. Now we need to substitute this. But instead of taking tan hyperbolic of this, is someone saying something? No? Yeah. So, yeah. So here, this value mu b by kbt, which we calculated, is 10 to the power minus 4, means it's very small than 1. And in the derivation also, if you would have seen, that when this value is very small, then actually what happens is tan hyperbola of say theta, any angle, if we expand it in terms of theta, the expansion is something like this, and so on. There are many terms. But if this theta is very small value, then its powers will be even more smaller. So that's why if the theta or the angle is very small, then we can just ignore these other expansions and consider it this. So here also, since mu b by kbt, which here would be the theta, its value is very small than 1, so we can take it as tan hyperbolic. So magnetization expression we can calculate using this. This is the expression. And since we saw tan hyperbola of theta, when theta is very small, we can ignore these higher order terms, and this will be just theta. Okay. So here also, we can write it as n times mu b by kbt. Okay. I hope this is clear. And then we'll just put in the formula paramagnetic salt 10 to the power 26 ions per meter cube, 10 to the power 26. Magnetic moment is 0.1 times Bohr magneton. Bohr magneton value is 9.27. Bohr magneton is 9.27, 10 to the power minus 24. And this is 2 square. And magnetic field is 1 Tesla. Actually, we had already calculated mu b by kbt. We don't need to do it again. Mu b by kbt was this, 2.2391. 2.2391 times 10 to the power minus 4. Okay, and this will also not be there. So mu b by kbt we had already calculated. So the direct value I am putting here. This is this, and mu is 0.1 times 9.27 10 to the minus 24. So when we calculate this thing, we will get multiplied by 9.27 multiplied by 0.1 is 2.075 or 6 or rounding up, and the powers will be 10 to the power 26 minus 24 minus 4. So it will be 2.076 10 to the power minus 2. The answers are all in decimals, so okay, this will be 0.02076, or if we are just rounding it off, all the answers are up to second decimal digit, so we will do that, and then this will be 0.02 ampere per meter, because it's magnetization. 0.02 ampere per meter will be the correct answer. Okay, next question. A system of electron spins is placed in a magnetic field of 2 Weber per meter square. So I told you magnetic flux density, its one unit is Tesla, or it's also 1 Weber per meter square. So it's the same. So this is the magnetic field given at temperature T under equilibrium condition. The number of spins parallel to magnetic field is twice as large as number of anti-parallel spins. The number of parallel spins is double the number of anti-parallel spins. Spins mean magnetic moments actually. Because in ferromagnetism, when we'll discuss, we'll see why we are calling spin, because spin angular momentum is considered there, unlike diamagnetism where we were only talking about orbital angular momentum, and because of that orbital magnetic moment. So when we consider spin angular momentum and spin magnetic moment, or simply we just call it spin, basically it's magnetic moment here. Okay? So if when we apply this field, some moments get aligned along the direction of field and some gets aligned in opposite direction to the field. And the situation is that number of spins or magnetic moments parallel to field are double the number of spins anti-parallel to the direction of field under equilibrium condition. Determine the temperature at which this is happening. Okay, so if Np is the number of magnetic moments parallel, then its energy, when this is field, usually we use H, or okay, in this case B, then the energy of spin when it's parallel, the energy is given by magnetic moment of this dipole and the field. If it's B, then B. If it's H, then H. So this is the energy. And if the magnetic moment is anti-parallel, then its energy is minus mu B. Okay. So for the parallel magnetic moment, the energy, if I'll call it EP, it will be, if it is for electron, then I can also call it mu B, Bohr magneton, and then multiplied by the magnetic field. So this will be the energy. And for anti-parallel magnetic moments, the energy, let's call it EA, will be minus mu B B. Magnitude will be same, the sign will be negative. Okay. Now we have to calculate the temperature. What we can do here is, we can take because it's given at equilibrium, we can apply this. That the number of parallel spins, the ratio of number of parallel spins to total number of spins, this expression from Boltzmann statistics, it will be e to the power the energy, which is mu B B. Energy of what? This was energy of parallel magnetic moment divided by kBt. And here it's a total. Total means number of parallel magnetic moments and number of anti-parallel magnetic moments. So then it will be e to the power E P by kBt. Here it will be e to the power E by EP by kBt plus e to the power minus E A by kBt. Okay. So when we keep EP is mu BB divided by kBt. Here also it will be e to the power mu B by kBt. This will be e to this. And EA is minus mu B by kBt. So this is the ratio of number of magnetic moments parallel to that of total. Now if we calculate number of magnetic moments anti-parallel to that of total, then this will be the same formula. E to the power, and here it will be e to the power E2 by kBt divided by e to the power E1 by kBt plus e to the power E2 by kBt. This will be e to the power minus mu B by kBt divided by e to the power plus mu B by K dt. Don't get confused. This is in subscript because this is Bohr magneton mu B and this is magnetic field. Okay, then this plus e to the power minus mu B by KB. Now here this is like first equation 1 and this is equation 2. When we divide equation 1 by equation 2, oh, when I divide equation 1 by equation 2, look here, this is my equation 1 and this is equation 2. So I'll get NP by N, P by N divided by NA by N. That is NP by N. Right. Basically it will be NP by NA. Because from Boltzmann statistics we know at equilibrium we can write the ratios. We can write this like this, and then by taking the ratio of these two, we will get NP by NA. And this is left hand side, then right hand side it will become e to the power this divided by this. E to the power mu B by KBT divided by e to the power minus mu B by KBT. This when we will take to numerator, it will be e to the power mu B by KBT, and this will become plus, so it will be 2 mu B by KBT. Now it's already given that this NP, oh sorry, I changed to small to capital, I'm sorry. I mean it's the same thing, okay. I forgot and I changed to capital here. It's the same thing. So it's already given that number of magnetic moments parallel is double of number of anti-parallel. That means NP by NA is, because NP is 2 times NA, that's given in the question. So this will be NP by NA, wait, N just a second. What was the question? Parallel magnetic moment is twice as large as number of anti-parallel spins. This will be 2, and so expression will be like this, and when we will take, to get rid of this exponent, we will take natural log, and then it will be natural log 2 is equal to 2 mu BB by KBT, and natural log 2, okay, we come to it, but here natural log 2 is, or first finally we need to find T. So T, if I bring to left hand side, then I'll be left with 2 mu BB divided by KB, and this will come to denominator means natural log 2. So this I need to find out to get the temperature at which this is the situation about parallel magnetic moment and anti-parallel magnetic moment. So the temperature I will get is 2 times Bohr magneton, that is 9.27 times 10 to the power minus 24. Magnetic field is 2 Weber per meter square. What else we need? Divided by KB, natural log 2. KB is 1.38 times 10 to the power minus 23. Natural log 2. Natural log 2 is 0.693. 0.693. Putting these values and calculating. 2 times 9.27 times 2 divided by 1.38 divided by 0.693 is 38.77, and the powers 10 to the power minus 24 plus 23, that means 38.77 10 to the power minus 1 Kelvin. If to remove this will become 3.877 Kelvin. 3.877 Kelvin. 3.8. This is the correct answer. Okay. Next question is, a magnetic susceptibility of iron measured at 900 degrees centigrade is 2.5 times 10 to the power minus 4. Given Curie constant 3.25 10 to the power minus 2 per Kelvin. So in paramagnetic material, we know susceptibility is proportional to 1 over T, and if this we want to remove the proportionality symbol and put equation, then there will be some constant, some values there, and this is how we generally call it Curie's law, and this is Curie constant. That value is given actually. Okay, and given the Curie constant, find the Curie temperature of iron. Curie temperature, it's iron is ferromagnetic material. In detail next week it could be discussed, I think. What do we mean by a Curie temperature? It's actually a temperature below which the magnetic material has magnetic moment. We were talking about, right, the presence of permanent magnetic moment. Diamagnetic materials don't have it, but other materials which we call magnetic materials, they have permanent magnetic moment in them. But up to a certain temperature, after that temperature is crossed, those permanent magnetic moments, they get randomly oriented. So they lose they don't remain ferromagnetic or paramagnetic. For ferromagnetic material, the Curie temperature is the value below which it's ferromagnetic, but above which it's paramagnetic. Okay, in ferromagnetism we'll discuss later. Okay. So the net spontaneous magnetization thing is lost and its behavior changes. Okay, anyway, so we'll be here. And for ferromagnetic material, this was for paramagnetic material. For ferromagnetic material, the expression is like this. Chi is given, which is 2.5 times 10 to the power minus 4. C is 3.25 times 10 to the power minus 2. T we need to find out. And theta is the Curie temperature we need to find out actually. T is the present temperature, this T, which is 900 degrees centigrade. We need to change it to Kelvin. 273. That means 1. This is in 900 degrees centigrade. Change it into Kelvin, we'll add 273. Means this will be 1173 Kelvin. This will be 1173 Kelvin, and the Curie temperature we need to find out. Okay, this 1173 minus theta will be 3.25 10 to the power minus 2 divided by 2.5 times 10 to the power minus 4. 3.25 divided by 2.5 is 1.3, and this will be minus 2 plus 4, that means 10 to the power 2. Okay, now the theta will be, because we have 1173 minus theta is equal to 130. So theta will be 1173 minus 130. This will be the Curie temperature, and this will be 1173 minus 130. This will be 1043 Kelvin. So the Curie temperature is 1043 Kelvin for this material. A is the correct option. We have one more question, and the question is nickel is FCC. Wait, no, nickel is FCC and its lattice parameter given is 3.52 angstrom. Magnetic moment of nickel atom is 0.6 Bohr magneton. Calculate the saturation magnetization of nickel. We need to calculate the saturation magnetization of nickel. Number of atoms per unit volume, first we will see. So in FCC, these we had discussed in earlier sessions. FCC has atoms at the corners, one unit cell, all 8 corners. So there are 8 atoms sitting at the corners, but they are contributing within one unit cell. Their contribution is only 1/8. This all we have discussed earlier. So the atoms sitting at the corners, they are contributing 1/8, and we have 8 atoms sitting in the corner. So corner atoms in total is 1, and in FCC we have atoms sitting on the face of this cubic unit cell, and we have 6 faces, means 6 atoms on the face, each contributing half to within one unit cell. In total we have 3 contribution from the atoms on the face. So in total we have 4 atoms in FCC. So there are 4 atoms, and the volume of FCC will be AQ, that is 3.52 angstrom 10 to the power minus 10 meter, and then we have to take cube of it. So this will give us number of atoms per unit volume. Okay, so this is number of atoms per unit volume. Now to calculate saturation magnetization, here it will be number of atoms per unit volume and magnetic moment. Number of atoms per unit volume is this 3.52 times, I'll go to next page. So magnetization is number of atoms per unit volume and magnetic moment of one atom. Number of atoms per unit volume is 4 divided by 3.52 times 10 to the power minus 10 whole cube, and magnetic moment is 0.6 Bohr magneton. 0.6, and Bohr magneton is 9.27. 9.27 times 10 to the power minus 24 ampere per square. When we will do this calculation, it will be 4 times 0.6 times 9.27 divided by 3.52. This will be 0.5101, and the powers will be 10 to the power minus 24, and in denominator we have 10 to the power minus 30. This will become plus 30 in numerator, and then 0.5101. 30 minus 24 means 10 to the power 6, and if I move this decimal point, then it will be 5.101 times 10 to the power 5 ampere per meter, the SI unit of magnetization. And the option that matches is option A. So these were the questions on based on the magnetic properties of solids that was discussed. You can refer all the derivations, Langevin classical theory for paramagnetism, the quantum theory, and the diamagnetic theories. If you have any doubt, we can discuss in next session also. But otherwise, further we are going to discuss the ferromagnetism, origin of ferromagnetism in material, and maybe other magnetic materials as well in the next week. You'll find it next week's lecture. Next more question, then we can end today's session also. I'll first stop the recording.